Okay, good afternoon, everybody. My name is Seogu Chun from Korea University Material Science Program. I'm actually one of the moderator in this event. And unfortunately, Professor Ji-hwan Kim, his flight was delayed, and then I just got a message from him. He just landed. So we'll just start without him today. Anyway, so it's my great honor to host this event here. So before we start today's event, the COPUST, the Korea Federation of Science and Technology, who is the sponsor, they pay everything for us, the stay and eating and dinner and also all the honorarium. So I want to give special thanks to COPUST, and then we'll watch the 7-minute video of COPUST, and then we'll start today's conference.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X-Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. BrainLink X-Lab Day establishes a global science and technology network among overseas scholars and Korean researchers. And in 2022 and 2023, a total of 24 BrainLink X-Lab Day sessions were held in each technical field, with 787 participants, including 161 from overseas and 626 from Korea, building a global human network. Also, talk concerts, one-day public seminars, were held in collaboration with the 2 nights and 3 days of BrainLink X-Lab Day to enrich their experience. In 2024, BrainLink X-Lab Day will be joined by globally renowned scholars, including Professor Luke Pyeong-se Lee of Harvard Medical School in the field of nanobiophotoниcs, Professor Ji-hwan Kim of MIT in the field of nanotechnologies, Professor Andrew Goodwin of University of Oxford in the field of materials chemistry, Emeritus Professor Teruo Okano of Tokyo Women's Medical University in the field of regenerative medicine, Jeffrey Newmark of NASA Goddard Space Flight Center Research Astrophysics in the field of solar physics, and Professor Dan I. Anderson of Uppsala University in the field of antibiotics resistance. The discussions will span 12 national strategic technology fields, pivotal to Korea's advancement, including the 3 game changers: quantum mechanics, nuclear technology, and AI. The event will see the participation of 40 Korean and international scientists and engineers. With 2 organizers leading each technical segment, the gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. And talk concerts will be held in collaboration with all BrainLink XLab Day sessions. The focus of XLab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each XLab Day session to ensure ongoing dialogue among attendees and promote collaborative research. To ensure that today's dialogue becomes the seed for tomorrow's magnificent achievements in scientific and technological development, COAST supports the reinforcement and expansion of the networks established through XLab Day. COAST, the organizer of XLab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the Fourth Industrial Revolution, where science and technology spearhead groundbreaking challenges, COAST remains dedicated to its role as a facilitator of scientific and technological innovations.
안녕하십니까. 한국과학기술단체 총연합회 회장 이태식입니다. 과총은 사회참여 확대와 권익신장을 도모하기 위해서 1966년 설립한 공익법인으로서 과학기술단체 육성 지원과 다양한 정책 연구, 기획, 조사, 자문을 통해 과학기술 발전에 기여하고 있습니다. 저는 2023년 과총회장으로 취임하여 새로운 도약을 위한 비전 프라이드 코스를 선언하였으며 이를 실현하기 위한 운영 목표와 추진 전략을 중심으로 빛나는 100년을 향해 모든 역량을 집중해 나가고 있습니다. 더 나아가 우리나라가 미래 핵심 기술 분야를 선도하는 기술 주권 국가로 자리매김하도록 국가적인 원팀 플레이를 이루는 데 있어 강력한 조력자가 되겠습니다. 대단히 감사합니다.
In this era of technological dominance, we will navigate through the fierce competition by fostering global cooperation in the fields of science and technology. BrainLink XLab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making XLab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink XLab Day.
Okay, I believe that video explains about this BrainLink XLab Day, the history and then the scope. So actually, I believe this event is similar to Golden Conference, which facilitates the friendship and then free discussion of science and technology. So anyway, I give special thanks to the COAST to give us this opportunity that I can bring the world-renowned domestic and also international scholars here, especially in the topic of development of neuromopic memristor for next generation semiconductor. So before I start today's events, I want to introduce you our honorable guests first. So Professor Joshua Yang from USC, can you stand up? and Professor Kyusang Lee from University of Virginia. Professor Tae-sik Yoon, the head of University Department of Semiconductor. and Professor Joo-Hoon Kang from Sungkyunkwan University, and Professor Sung-Kyu Kim from Sejong University. Also, to sponsor from Korea University Material Science, I think Professor In-Han Lee, the department head, and also BK21 director, Professor Soo-Young Kim is also here. Okay, so anyway, this talk concert is kind of pre-meeting of BrainLink BrainLink conference, which is for 2 days, 3 nights. We'll share our presentations, and also it's more like closed presentation, like Golden Conference. But this BrainLink X-Lab Day talk concert today, this event is more like public service, which is open to students and general audiences. So I think this will be great opportunity, so we can share the visions and directions of this research field to open publics. And actually, I found this is very surprised that this there is more than 87 pre-registered people. They show interest to join this concert. So in the next 2 hours, our meeting today, this talk concert will follow this sequence. First, there are 5 speakers. They'll give about 10 minutes talk. Actually, we already gave them the topic. What is your perspective of future direction of AI semiconductor or neuromorphic device? So we'll listen to their talks, and then if you have the question, after finishing these 5 talks, after the break, we'll have panel discussion. So you can give them freely about the question, what they presented, or any other question you are interested in. Also, I received some questions that when people register this event, and some people actually send us online questions. So I believe those questionnaire sheet is already in front of those panels. So we'll also discuss about that. Okay, so other than that, I'm really happy to bring my friends and top scientists to this event. And even though the weather is very hot and humid, it will never break our friendship or our passion to continue our research. Thank you very much. So I'll give mic to Professor Soo-Young Kim. He will host the presentations.
Thank you, Professor Seo-Gu-jeon. Hello, my name is Soo-Young Kim from Korea University. This is my honor to serve as a chairman for this famous workshop. As Professor Jeon Woo-sun announced before, 5 very famous speakers are ready to share their recent work. I'm pretty sure that all of us can get many recent knowledge about the neuromorphic memristor today. So the first speaker is Professor Joshua Yang. Can you prepare for your presentation? Joshua Yang got a BS degree from Southeast University and PhD degree from University of Wisconsin-Madison. And he worked HP lab as a principal researcher, and he joined University of Southern California at 2020. And let's welcome him with big hands.
Thank you. Laser pointer, yeah. Okay. Laser pointer. This is just flip. That's okay. Okay, thank you. Thank you, Professor Kim, for the introduction. Thanks, Professor Jeong and others for organizing this very interesting event and your kind invitation to be here today. I think for the afternoon session, my understanding is it's going to be at a very high level. So what I'm going to talk about is a few slides at a very high level talking about why we want to use memristors for neuromorphic computing. And for those experts in this field, you already know all those. I apologize for that. I'm going to stay at a very high level, talk about the motivation. So first, why we are interested in this topic? The reason is really because the digital hardware we are using is way behind the demand for AI, for machine learning. As shown by this plot, you can see the x-axis is time. The y-axis is computing performance demand for running a certain neural network model or AI. So the y-axis is measured as petaflops days, meaning if you train a certain AI model, how many petaflops you need for how many days to finish it. And that's the y-axis. Basically, the performance demand was normal 10 years ago. As you can see here, about 10 years ago, the demand doubled every 2 years, roughly, similar as Moore's law. So scaling the device by Moore's law can pretty much meet the demand. That was about a decade ago, but since from here, you can see the AI started to show great promise, and the slope increased dramatically. The demand for computing performance doubled every 3.5 months. Okay, so in the last few years, every one of us know things started to go crazy when the large language model, such as ChatGPT, started to show magic. And you can see now the demand for computing performance doubled every 2 months instead of 2 years. Okay, so in order to train a ChatGPT-3 model, OpenAI needed to run 9,200 GPUs for 2 weeks, which will cost $4.6 million and around 1 gigawatt hour power, which is equivalent to the emission of 450 tons of CO2. And that's old version. For the newer version, GPT-4, OpenAI needed to run 25,000, the state-of-the-art GPUs for 3 months, which cost $63 million. That's for training the model. For running the model for inference daily, it costs $700,000 for running it daily. So the reason it is so costly is not really the software to blame on. Really, it is our hardware has not been making as much progress as we want, as we need. So what's wrong with our hardware? At the device level, we are facing a few wars. As every one of us know that Moore's law is coming to an end. That's the first war at the device level. And also, the performance between the memory and the processor, there's a gap. The memory is behind. The memory is the bottleneck, and this gap is increasing over time, not decreasing. So that's the so-called memory wall. That's the second barrier we have at the device level. The third one is the heat wall. Basically, even though we can still make the device smaller and smaller, but the issue is when you make them smaller, the power density used to be constant when you make the device smaller, but now actually when you make them smaller, the power density increases dramatically. Even if you can cram more devices on the same chip area, because power is so much higher, you're going to melt the chip very soon. So you cannot turn on all the devices on the chip. You turn them on all together same time, they're going to melt the chip. So that's the scaling ended, and so that's the third war at the device level. But at the architecture level, the barrier is as big, if not bigger. That is the Neumann bottleneck. So we all know that our current computing system, including your phone, your iPad, your laptop, and the supercomputer, they are all based on. It has a separate and the memory. These two are physically separate. So you store your information in the memory. When you need to process it, you send it to the processor. You get it processed. You get the result. You send the result back, store in the memory. You take the next piece of data to the processor. So this is a sequential process, and you need to move data between the two units frequently, which was perfectly fine in the past when computing did not involve a lot of data. But nowadays we know the computing, especially machine learning, AI, they are data-centric. Then constantly moving data between these two units become a much bigger problem, consume a lot of time, a lot of energy. So that is why our current computing architecture is not efficient either. And in addition, it's a purely digital system. Our world is analog. So you also need to convert the analog data into digital first in order to be processed by this Neumann architecture system. So how to solve the problem? We learn from the most efficient computing system known so far, which is our brain, actually. So how does the brain do computing? The brain consumes much less energy. How does it achieve that? The brain does computing within a neural network, like this. A neural network is a network of neurons connected by the synapse. So the synapse is a memory here, and it's connected to neurons. And so the computing happens in the neural network, and the computing happens where the data is stored, which is in the synapse. So it is a in-memory computing. You don't need to move data a lot. So that is a huge deal, save a lot of time and energy. And also in the brain, the computing happens everywhere simultaneously. It's a parallel computing instead of sequential. And it can deal with analog data directly. It is analog computing. So with these three principles, we can have a computer with much higher efficiency, time efficiency, energy efficiency, okay? There is more. Actually, the brain uses neuroscience principles for computing, which is very different from our current machine learning. That make it also efficient in learning and have a higher level of intelligence. So if the devices we use to build the artificial computing system can implement all these four principles, it will be much more efficient and also with a higher level of intelligence. So in order to do that, we will need a new type of devices other than just the traditional CMOS device. So that's the memristor devices. Using memristor devices for computing has been the research focus of my group in the last few years. Some of our major results are summarized here, which can be categorized into three groups. So in the first group, we're trying to build a machine learning accelerator. Okay, so the goal of this is just to get a higher energy efficiency, higher throughput for the computing system. In the second category, we're trying to build artificial synapse, artificial neurons using the memristor devices. And with those, we can build artificial neural network that are biorealistic, so that it can also implement the neuroscience principles. The goal here is to get a higher level of intelligence in addition to energy and throughput improvement. In the third category, we're trying to build a toolkit for intelligent systems, such as build a system that can directly interface with the sensors. And as shown by this example, you can have a sensor talk to your memristor processor within analog domain without the need of the ADC-DAC conversion, and the sensor can directly power the memristor system so that it's a self-powered system as well. So those are the focus. So I'm going to stop here. If you are interested in this topic, I also recommend two special issues I edited last year on neuromorphic computing. So the first one is in the IEEE journal, Electron Devices. The second one is Advanced Materials. There are a lot of interesting articles on this topic. So I'm going to stop here and looking forward to more discussions later. Yeah.
Thank you for the great presentation, Professor Joshua Yang. Even though you have many questions about this slide, but we have the discussion time, so just keep in mind that you can ask it later. Okay, the second speaker is Professor Kyu-sang Lee from University of Virginia. He got a BS degree from Korea University and MS degree from the Johns Hopkins University and PhD degree from University of Michigan. And he worked at University of Michigan as a postdoctoral fellow, and he joined University of Virginia from 2017. So let's welcome him with big hands.
Thank you very much for inviting me here to give me an opportunity to present some of my work and then introduce some motivation to work together. Today I'm going to talk about the heterogeneous integration toward the intelligent sensing. So I'm going to more focusing on the application side, since I knew that Joshua will cover very broadly about the computing, and then he will give a nice introduction about this neurocomputing. So I'm going to kind of introduce where we can use, and then why we need to collaborate, and what type of the segment we need to develop this type of application. First, I'm going to start with some of the application very recently demonstrated by the Figure and OpenAI. So basically, it's combination of the robotics and the large language model to demonstrate the functionality of the AI toward the actual kind of application for the humanoid.
Great. Can I have something to eat?
Sure thing.
So this is the very quick demo. So but I just cut the video into the short kind of the segment. So basically, this guy's talking to the robot, so that this robot is recognize what he ordered and then he react. So to achieve these functionalities, the first we need to have a sensors. Second, we need to have a hardware to process these signals. Also the implemented algorithm, and then we need to react, such as we need to have image sensors, skin, and then mechanics. So basically we need a lot of the component to demonstrate the actual application, even just using the neuromorphic computing or the AI algorithm. So we need to integrate them into the single system. So if you compare the human and then artificial intelligence, we can kind of think about especially the sensing part, which means that we have 5 senses, so such as touch, hearing, taste, smell, vision. But if you're looking into the artificial intelligence, we can kind of separate 2 parts. One is the training part. As Professor Joshua mentioned, it consumes a lot of powers and requires a huge computing powers. And we also need the inference, which means that we need to kind of learn this kind of algorithm on sensor, on device, to process this signal based on the trained data. So for the inference, we probably need less kind of the computing intense processors, such as the neural processor engine or the memristor-based processors, so that we can do the inference at the sensor integrated platform. So edge intelligence, what those kind of the new hardware, which means the emerging device, can play a role compared to the conventional system. So if you're looking into conventional system, you have a sensors, and then you have some peripheral circuit, and you go to the memory and you do the processing unit, process it. But the edge intelligence, what we can do is, as Professor Joshua very briefly mentioned, those sensors can receive the data, and at the same time it can process. So we can kind of think about the processing in memory or computing in memory, and then it can come to the external circuit for the further processing. So this is the basic concept of the edge intelligence. And to demonstrate this edge intelligence, we can kind of think about what type of the technology from the variety of the experts. For example, so we need the first materials, we need a device, and we need the architecture and circuit to combine this device into the system. Also, we need the packaging technology, and then we need to implement the algorithm, and then we can have some system level demonstration. So I'm going to very briefly cover each part of this component. Is mostly my research work. The first, the materials. So we need the functional material which can act as the sensors, computing unit, or the memory. So what we have developed is called the remote epitaxy. So basically, we want to develop this membrane type of the material that can be stacked, that can be deformed into any shape of the platform. So what we have done is that we use the crystalline material to achieve the highest performance. So what we have done is we use the semiconductor, and then we cover with a 2D material, and then we peel up this membrane, and then this membrane can be stacked or deformed into any shape. So we started this work from 2016, worked with one of the moderators, Ji-Hwan Kim at MIT. So we developed a bunch of the different type of the material. Actually, 2018, I spin off the company that is focusing on the gallium nitride toward the industrialization. So what the first step is that we need the functional material. Then what is the next? We need a device. So especially synaptic device is very powerful to process these kind of the signal in energy efficient way. So if you have a synaptic device, especially for the sensory application, we can combine this sensor device such as the photodiode, pressure sensor with this synaptic device to achieve this sensory neuron or the sensory synapse. Eventually, what we want to achieve is the sensory synapses that is fuse the functionality of the synapse and then kind of the sensor, so that we can have the single device to function as a sensory neuron or the sensory synapse. Then what we need, so computing. So Professor Joshua mentioned the memristor-based device, but we can also achieve using the CMOS technology as well, so which is a pre-merger technology. Here I'm using the CMOS-based embedded flash memory, but it doesn't need to be limited to this flash memory, but you can use the DRAM, SRAM, whatever you want. So here, we adopt this architecture first, and then we tape out this SRAM-based CMOS chip. Then for the difference between this kind of the powerful GPU versus the in-sensor computing is that we need to have a very simple artificial neural network to operate them on the sensors. So which means that we first design the DNN, which means the 100 layer of the deep neural network, then we condense it into the very small number of layers, which is the condensed ANN design. Then we need to compile those kind of ANN neural network that can be implemented on these powerful, not powerful, but very efficient, power efficient memory-based chip. So this is the computing part. Once you demonstrate the computing part, that next step is the packaging. So probably everyone heard about the HBM, so which means that you need to integrate the memory or the computing unit or the power unit into the single system. To demonstrate that, we need a very advanced packaging technology such as the hybrid bonding between the two different type of material, or one of the very advanced technologies, the TSV, so which means the through via hole based through the silicon, so that you can integrate them into the 2.5D or the 3D integration into the vertical or the lateral way. So this packaging technology is very important, especially if you need to combine with this kind of the heat dissipator to kind of efficiently operate the chip. Then what's next? We need to integrate this emerging material or the emerging device with the CMOS technology. So this is one of the example of the program that is supported by the NIST called the Nanotechnology Accelerator Program. So like the 12 to 14 university and institute collaborate, and then we tape out the single chip that combine the many different type of the designs, such as the two-terminal device, three-terminal device, and then backplane circuit for the display, backplane circuit for the photodetectors. What unique part of this process is this is the tape-out process, which means the CMOS-based process, and then this is finished that can be integrated with directly integrate the new material or the new device, which means this is tape out by the Skywater technology, but we collaborate with the Google and then the Western Digital to tape out these 8-inch whole wafers, just kind of collaborate with the emerging technology from the material scientists and then electrical engineering to adopt this technology for the combined with the CMOS, so that we can fuse this functionality, which is called the CMOS plus X. Then application. This is one of the demonstration that my lab is recently demonstrated this year. I published in Science Robotics. What we have done is that we integrate these two image sensors that have functionality to encode the signal directly by combining the memristor and the photodetector. And at the sensor, we encode the data, and then back end of the sensor, which is the near sensor processing, we adopted these microprocessors that implement the artificial neural network to process these signals. So eventually, we were able to do the 3D object tracking using this neuromorphic system that mimic the insect eyes. What we have done is we have the sensors, which is the kind of the conventional system, like you can imagine the photodetector. That sensor is combined with the artificial synapse, here the memristor. So we have two different type of sensors, so we demonstrate the stereoscopic eyes. And at the sensors, using this synapse, we pre-process the signal. The next step is we use the microprocessors to post-process this encoded signal at this chip. Then we can have some meaningful information. Here, the next generation of the sensors or AIoT device require the multimodality, which means that we have multiple sensors. What we need is we need a very special kind of neural network as well. So here we only adopted the two different type of sensor integrated with this artificial neural network. So to adapt it, we adopted called the federated split neural network, which means that we split the neural network into the multiple sensors, and then we fuse those neural network at this processor, which means that we can have this condensed neural network from the multiple device into the single system. Eventually, we can achieve the final signals that we want to process. So, what is the real advantage of this chip is that we can simplify the conventional process system, which means the very complicated digital-based system, into this very simple analog-based computing system. Eventually, at the post-process, we can use this simplified neural network compared to the deep neural network, so that we can achieve the energy efficient and then latency efficient type of the processing. So that is the beauty of this edge intelligence. You can save the powers at the in-situ type of manner of the processing. So that this is one of the examples we can track this signal at the 3D space very efficiently, even compared with the conventional system. And then what is next? So we want to demonstrate this robotics, which means not only the signal processing, we need to react. So this requires a different type of the semiconductor, which means that we need to powering this muscle or the motor. So we adopted called the gallium nitride, which is the widely used power electronic system. But we integrate this synaptic behavior using these ferroelectric materials. So which means not only we can mimic the computing, which means the brain, but we can kind of integrate for the motion as well. So I'm not going to cover the details, but this one can power the muscle, which means to power the motor of the system. So eventually what we want to adopt this artificial intelligence toward the robotics, we want a sensor, which means the in-sensor computing, and then we want to do the near-sensor computing to process the more complicated neural network. Then eventually we can do the mechanical operation. This is one of the examples that why we need this multiple component, which is the artificial eye, which mimic the human eye's motion. So what we need is first, we need optics. Second, we need optoelectronics. Third, we need computing, which means the neuromorphic computing. Then we need to combine with the mechanics as well to demonstrate actual robotic platform. So to achieve this, we are kind of, my group is focusing on the very different type of this sensing platform combined with the computing platform. Eventually, we want to have a kind of those mechanical platform to integrate toward using this AI system for the robotics. So I have covered a little bit specific domain of this neuromorphic computing, but I know that Joshua covered very well for the computing part. So this is one of the application those neuromorphic computing can be used in the actual field, such as robotics or the biomedical application. Thank you very much for your attention.
Thank you for the great presentation. And next speaker is the Professor Tae-Sik Yoon from UNIST. He got BS, MS, and PhD degree from Seoul National University, and he worked at Samsung Electronics as a senior researcher, and he joined UNIST from 2021. And let's welcome him with big hands.
Thank you, Professor Kim. I'm also very thankful to the Professor John and the host for the nice opportunity to share our idea about this neuromorphic memristor together. And also, thank you very much for some brief and nice introduction about the neuromorphic system to Joshua Young and then Professor Lee gave. And now I'm going to talk about some materials for the memristors. And actually, the memristor can be used just as memory, kind of standalone memory, but also it can be used as some computational memory and also the synapses. So why I chose those titles is that even though we can study, investigate many types of materials and devices, but the one thing we have concern is that whether these materials can be integrated in the silicon platform. So that was the major concern. And every time I talk about some memristor, and then if I say that, okay, I study the memristor devices, and there's many semiconductor guys always ask whether it can be integrated in the silicon technologies. And also, what kind of materials you used. For example, you can use the silicon dioxide or silicon nitride or aluminum oxide or hafnium oxide. All of these materials are very common to the silicon technology. And then they are very positive to them. But if we use some novel materials, and then they have concern whether these materials can be integrated. But if you can make devices, very good devices can be used for the synapse in the neural network and also the computational memory. And if you can make devices with these kind of common materials, then it's okay. But it's very difficult. That's the reason we explore the new materials and new type of devices. So now I'm going to talk about the materials. And then the conclusion is that what I want to say is the semiconductor guys should be open to new materials nowadays. Even though they are very successful to use the silicon dioxide, silicon nitride, or common materials in semiconductor, but now even if you want to have a very good performance of the memory and synapse, and then we have to open to new materials. Okay, so as the previous speaker, Professor Yang and Professor Lee already discussed, we are in this data-centric application era because we generated a lot of data, so we need to process a lot of data, vast amount of data, very energy efficiently. And then even though we have successfully used the von Neumann architecture for the computation, but the problem is that we have a serious von Neumann bottleneck problems and also memory performance issues. If we use this von Neumann architecture for the computation, and then the processor keep access to the memory to get the data from the memory and then give the data to the memory. And if the processor access the outside the memory, and then the power consumption is greatly increased. So that's a problem. So what people are doing is that we want to integrate those memories in the processor unit together. So that's the reason we are interested in the 3D hetero integration, and also we are interested in some non-von Neumann architecture computing system like computation memory or processing memory. Also, neuromorphic system is also one of them because the neuromorphic system is kind of a combined structure system. And it means that the neuron and synapse are closely connected together, and then neuron can process information through the synapse, and then those information would be stored in the synapse. So it's very integrated system. So you can have some opportunity to solve the von Neumann-Bartlett problems. And then we have some question whether we can have those good memories for the computation. Because the CPU has a very high performance with high speed operations and then low power consumptions. And then the memory should have a similar properties. Otherwise, the memory cannot be integrated together as processing units. So we have some candidates as a memory like SRAM, DRAM, and flash, and also we have some emerging memory. So all of these devices has pros and cons. For example, the SRAM device has a very good performance because it is made with some CMOS. But problem is it's volatile and also it's a low density. It's a low density because we need many transistors to get the one SRAM cell. And also it has a limitation in the digital type operations. So at the beginning, people tried to make some neuromorphic system with the SRAM because the SRAM has a very good performance because it's composed of the CMOS. But problem is that the density is very low. So if you make a SRAM synapse and then your synapse density cannot be increased too much. And then we need another memory outside the CPU, and then you also have the same problem of von Neumann-Bartlett. Also, DRAM is also it can be a good candidate because it's a very high density. The problem is that it is so volatile, and then the stored information keep lost, so we need always some differential operations, and also it's a digital type operations. And one of the problems is that the DRAM is not easily integrated on the CMOS platform because the device structure is very different, because it needs very large capacitors. And also, even though people try to make us an embedded DRAM with some 2T06 structures, but still it's a very unmatured state. In the memory side, like a chip density size, bit density size, the flash memory is a champion actually. It's very high chip density, bit density, and also low bit cost. But the problem is that the flash memory operation voltage is very high, and also speed is very low. So if we use the flash memory itself as some synapse, and then we may have some problem of the performance gap between the processor and the synapse. Also, we have some candidate of the emerging device, but it's just an emerging device. So it's not that mature to be integrated successfully for the reliable computing system, even though many people try to make some computing system with the emerging devices, but we have to solve many issues like reliability or uniformity or also the performance of these memories. Okay, so at the beginning, the memory is just for the storage. So when we talk about the memory, and we more focus on the density of the memories. But nowadays, people also consider the speed and performance of the memory because the memory is tried to be used for this computing system. So we have to consider the performance, memory performance, like low power operations and high speed and then good reliability and the multi-level computing opportunity in addition to just the density of the storage. Also, so I already discussed that we have some problem of von Neumann-Bartlett, and Professor Yang also discussed that we need to adopt a new type of architecture, not von Neumann architecture like a computational memory, a computing memory, or some neuromorphic system. And then we have some opportunity of those devices, including the conventional SRAM, DRAM, and flash. Also, we have some emerging memories. And then always we have some concern about the compatibility, whether these devices can be integrated to the silicon platform. And the SRAM and DRAM flash is fine because those devices use very common materials which have been already confirmed to be good enough for the integration to silicon technology. But for the emerging device, we consider many new materials. And then we have a concern it is compatible to the silicon. But my idea and then my opinion to the semiconductor guys is that we have to be open to new materials because the performance is very important to realize those computation memory system, computing memory system, and neuromorphic system. So we have to open to many new type of materials. And then these emerging devices, emerging memory like RRAM or PRAM or ferroelectric tunnel junctions or spintronics, those devices could process the high density opportunity. Also, you can make those array structures and you can operate it. So vector matrix multiplication operation, which is very common for the artificial intelligence computing. And then if you use those emerging memories, and you can easily realize those architecture and those computing systems. So that's the reason we are interested in the memristor, because this memristor device can realize those architectures. And then we also consider what kind of a memristor can meet those requirements or those performance. So we need a high performance, and also we need a high reliability, which are comparable to the SRAM or DRAM. Then we have more opportunity for employing those new devices in the silicon technologies. So we have to realize those synapse performance or memory performance, including the high density network of neuron synapse and neuron structures, and also overcoming these some binary operation of SRAM and DRAM is good to make some analog or multi-level and linear, symmetric, and uniform change of memory state. That is very beneficial for the those non-conventional computing. Also, for some spiking neural network application, we need some time and pulse condition dependent properties. And also, we at the beginning, the Professor Yang shows that we have a very concern about high power consumption, high energy consumption for this AI computing if we use the conventional SM and GPU and CPU. And then we have to reduce the operation powers, like some human brain level, and that would be great. So we have to reduce the powers. And also one thing is the silicon compatibility. But I want to say that people should be open to those issues. Even if we have some problem in the silicon compatibility of doing new materials, and then so far, the semiconductor guys dropped those materials because it cannot be integrated the silicon platform. But for the manufacturing side, I understand, I accept those ideas because the manufacturing guys are very much conservative because the processing and device yield is the most important criterion for the manufacturing. But for the R&D and then for the new technology development, and we have to be open to these compatibility issues. And the 3D integration is very important because we want to make an integrated system of memory and synapse, and memory and processors. And the process should be fabricated on the silicon platform because the silicon is the best device so far. And then those new memories should be integrated in the three-dimensional architectures. So 3D integration is very important, and then those devices should be compatible to the learning algorithms. And the one thing which is very important is the high reliability with uniform synaptic properties. Because we use the memristor or phase change memory or ferroelectrics, and those materials are kind of changeable materials. We use the state change of those materials. And then so far, the semiconductor guys try to make some unchangeable device, like for the silicon CMOS, and then their purpose is that VT should be shifted, should not be shifted. For those in emerging memory, we try to change the material state to make some memory operations. And then, all of these material changes stochastic. Include for the RRAM or PRAM, it doesn't matter. All the materials, all the devices has some stochastic change of material state. And then whether we can make some highly reliable and highly uniform synaptic device or memory device, that is very important. Also, I told that the 3D integration is very important, and then those devices should be integrated in the back end of the line. And the back end of the line integration issue should be also considered, like parasitic resistance in the metal line if we make a high density, high integrated array. And then also integration with the two-terminal selector, three-terminal transistor switch for the reliable array operations. And also if you make some device on the back end of the line, and then processing condition is also important, like low temperature processing. But the performance should be also good enough, even we process at the low temperature. So process condition is also important. CMOS compatibility. For some researcher who working on some artificial synapse device with some ionic operations, and the people try to use the lithium ion or hydrogen ion. And we know that those ions are kind of very dangerous material for the silicon. But if the device performance is good enough, and then you can use those ions. And then the job we have done is that we have to solve those compatibility issues, like passivating those devices and preventing the diffusion out of those ions. So we have to try to solve those problems, not just dropping those new materials. And so I think that we have so many opportunities like materials and structural engineering. At the beginning, many RLM guys, for example, use the only single layer of materials. But in order to improve the performance, people try to employ the new structures like a bilayer or new processing schemes. And also, you can use many type of some mechanism like action ion distributions and the interfacial reactions and the energy barrier modulation at the interface. And also, we have some possibility of processing and operation engineering. I told you that we have some issues of the uniformity and reliability because we use this stochastic change of materials. But that also was the problem even in the very conventional flash memory device. You know, the flash memory device use the threshold voltage shift for the memory operations, and then those threshold voltage shift is proportional to the charge density in the floating gate or charge trap layer. And those tunneling for the charge storage is also very stochastic. So people try to use some operations, new operation schemes like some program and verification method. So because we use the stochastic phenomena of the material change, and we also developed new operation schemes to improve the reliability and uniformity. So those some issues and those opportunities, the pros and the cons that we can have for some materials for the synapse. So I want to say that even though many semiconductor guys worry about that those emerging devices are some limitation or challenges of the compatibility and the performance, but I want to say that we are open to the new materials and that we are trying to explore the new materials to improve the device performance. Yeah, that's all, and thank you very much for your attention.
Thank you for the nice talk in viewpoint of the material science. And next speaker is Professor Ju-Hoon Kang from Seongkyungwan University. He got BS and MS degree from Yonsei University and PhD degree from Northwestern University. After finishing the postdoc at UC Berkeley, he joined Seongkyungwan University at 2019. And let's welcome him with big hands.
Okay, thank you very much for your kind attention, and thank you very much for the wonderful event organization, and I'm very glad to share my research work. So today I'm going to talk about a little bit more about the materials, so like the other professors introduced next generation electronic devices, but my goal in my lab is more about the material side. How can we produce like nanomaterials which can generate synergetic effect by hybridizing with the silicon-based materials. So today I'm going to talk about 2D semiconductors, especially processed in solution. So here you can see we all know that the physical limitation of the material itself can saturate the Moore's law, and then we have to think about how can we overcome that Moore's law or the physical limitation. So the first one is more and more concept we can make an integration of the silicon-based materials into the vertical direction, like a 3D architecture and the integration into the vertical direction. The other concept is the more concept, von Neumann and beyond the von Neumann, the device architectures, like including neuromorphic computing and the MEM transistors, memristors, and the integration of the sensor, memory, and then the processing unit. So in here, my goal is how can we process the low-dimensional nanomaterials to overcome or to utilize in these purposes. So my starting point is that from the material science philosophy, we're gonna start with this tetrahedron-based material science philosophy, the structure, property, processing, and the performance correlations. So as you can see here, the carbon has two different structures. The diamond is like a FCC cubic crystal structure, but the next one, carbon, is like a graphite structure. Because no one likes to make their own wedding ring with a carbon, like a pencil, like something strange black carbon-based structure, that means the diamond and the graphite has different crystal structure, and that gives us the different properties. So from the graphite, that layered structure provides us more the interesting properties like in electronics, optoelectronics, and etc. because of their layered structure. And then the atomically thin layer provides us the quantum confinement effect, and that can give us the exotic physical properties. And also we are interested in to process the other layered materials like these semiconducting materials, including BP, black phosphorus, or the TMDC. This is some well-known semiconducting 2D materials. And then based on these materials, we can generate a very exotic the physical properties and the next generation future electronics, including MEM transistors, neuromorphic computing, and the sensing applications. But my question is that in between those two, how can we process such accessible materials? And for the industrial level demonstration, how can we make it scalable production? And also, how can we secure the structural or the chemical purity? And also, process compatibility should be considerable here. And also, transfer, alignment, assembly, positioning is another issue you have to consider because their nanoscale, tiny material should be considered in these purposes. So my approach to address such issues is the solution-based synthesis of 2D semiconductors or the layered materials. Because this is a public kind of talk, so I'm going to more simplify my concept of my approach. First of all, we can take the materials. As you can see, that Lego block layered semiconductor shows that three-dimensional structure with the layered structures are vertically stacked, as you can see here in the middle. And then in a beaker, we exfoliate them and then stabilize as an ink form. And then we reassemble into the functional devices based on our approach into the desired structure to make the exotic electronic properties based on the functional device structure. So in realistic, as you can see here in this video, there's a layered crystal structure, and in between those two, we intentionally put something in between those two to minimize their interaction between the layers. Then, as you can see here, after the process is done, the layered structure is inflated like into the huge rock. That means something is intercalated between the layers, and then they can minimize the interactions between the layers. And then after that, this rock is sonicated with a very mild condition, then we can get a large amount of 2D sheets with atomically thin level. So this can be successfully coated with a nanometer scale, and then we can make the electronic devices which is going to be introduced in the later slide. So this advantage of solution-based processing is that we don't have to use any the high-end equipment. We just have the crystals and the solvent and voltmeter, and that's it. And the vacuum-free and a very simple process. And also we can do the mass production. As you can see here, tons of liters are producible in a very short time scale. And also we can make the thin film based on the obvious solution-based thin film processing for the device verification. And another advantages are here you can see that for the potential, the flexible or the stretchable electronics applications, we can deposit any arbitrary surfaces. And also since that material is partially overlapped to each other, so under the stretched condition, we can secure mechanical and electrical stability. And also there are several defects are formed during the process. So initially we thought about this as a kind of drawback of this approach, but ultimately we can control that, the defect or the calculate vacancy, like the electron doping process that can reversibly treat it, so we can generate additional functionalities, including memory applications or the charge trapping based non-volatile memory or some other applications. So that the thin film, we firstly demonstrate the transistor, very simple structure of a TFT structure. So there is the thin film of the 2D semiconductor on silicon dioxide, and then we apply the gate voltage plus minus 80 volt, and we can successfully turn on and off of this thin film, although that is the mosaic-like, the partially overlapped nanosheets assembled thin film. And also their metrics are quite interesting. The mobility is not that high, but still that's about 2, and the on-off ratio is 10⁶ on the silicon dioxide layer. So we are trying to scale up this for the industrial level, kind of industrial level. So 5-inch wafer, we utilize a slot die coater to coat dielectric and then this semiconducting 2D film sequentially, and in less than several seconds we can coat the both layers simultaneously. And then the high uniformity and the high, the energetic, the smooth surface can give us a very high carrier mobility, and with the high uniformity of these devices. And based on that, we also can expand that the methodology to exfoliate the materials in a beaker. We also expand the materials accessibility, including metallic graphene, and then another semiconducting hafnium disulfide. Here, the goal of the hafnium disulfide processing is that we have to apply the electrochemical potential to the intrinsically the conductive material. So to prepare the hafnium the oxidation layer, the insulating layer, like oxide, hafnium dioxide, we initially process semiconducting hafnium sulfide and then make a thin film, and then convert into the hafnium oxide, which is well-known high K dielectric for the dielectric layer purposes. So we assemble all together to generate the field effect transistors, diode, and the photo transistors, and some simple logic gates in a wafer scale. And as you can see here, the cross-sectional image overall, the thickness of devices are less than 10 nanometer thick. So we are now trying to stack up into the 3D vertical integration of such devices. And also the defect, what I mentioned, the defect, which can be the huge drawback during the solution-based processing, but fortunately we can passivate them by chemical treatment. So here we can make a thin film of MOS2 as a semiconducting channel, and also we can partially chemical treatment the area selective doping here. So the underneath of a source and drain layer, there's the chemically doped, and otherwise there's the high number of the defect concentration is exposed to here. So based on that, the defect concentration, we can also control the work function of the channel, and based on the gate voltage applications, so initially there's nothing, and then at around the 0 volt, the saturated point is observed, and then another point is observed beyond the 10 volt of the gate voltage. So this can be utilized like a ternary logic gate. And also the vacancy, the controlled layer is interfacing between the source and drain layer and with the conventional semiconducting layer, which is called as, which is the simple structure of a MOSFET structure, but we place this vacancy control the semiconducting layer in between this electrode and the semiconducting channel to generate more device functionalities, including multi-state transistors, and also the non-volatile memory. And based on this memory behavior, we also generate the neuromorphic device performances. And that since these materials are solution-based process, and also the ink-like a form, final structure is just an ink-like form. As you can see here, hafnium sulfide and moly sulfide and graphene are prepared like a stable dispersion as an ink in alcohol. So we can sequentially deposit based on by using the inkjet printing technology, which is a very simple technique to deposit without lithography manner. So sequentially printed diamonds shows quite decent properties like mobility is less than 10, and also on-off ratio is about 10 to 6. But still, the limitation of this approach is that the resolution is quite poor. So we have to achieve more than hundreds of a micrometer channel length, which is not very ideal for the integration purposes. So now we are working on the how can we integrate heterogeneous materials into the vertical direction without like damaging the underlying layers when we patterning the upper layers. So since again this is a ink-like form, we can add any additives with a trace amount of them. So we can add the diazide, which is a UV curable, the cross-linker. So trace amount of a diazide can grab the upper layers and under layer by expose the UV light, and we can successfully patterning molysulfide and the upper graphene layers, and then by reiteration of that process, we can stack up the multi-layered device. Integration is available in these purposes. Okay, so the summary of my talk is that we are looking at how can we bridge between the fundamental nanomaterials properties and practical demonstrations by filling out these triangle to try to expand the 2D materials library we can access, and also their quality, quantity, and the purity should be secured well. And then we have to assemble into larger scale with the desired structure. And by filling out this triangle, I believe that their very outstanding fundamental properties of nanomaterials can be transferred into the industrial level, the product. Okay, thank you for your listening.
Yes, thank you for the nice presentation. And this the last speaker of first stage in this workshop will be given by Professor Seong-Kyu Kim. He got BS from Seongkyungwan University and MS and PhD degree from KAIST. He worked at Northwestern University, Clemson University, and MIT as a postdoctoral researcher, and he joined Sejong University in 2020. Let's welcome him with big hands.
Thank you. I really appreciate for giving me this opportunity to share my research with you. Before starting my talk, I think everybody wants a coffee break. I just checked it. Break time is just 10 minutes, so I hope you enjoy my talk as a break. So my talk is not difficult, but the previous speaker gave us very proper and also important information about the neuromorphic and memristor and also material science. So I just focused on the characterization of memristor device and also failure analysis. My title is Atomic Level Approaches for Identifying Switching Phenomena in memristor device. And my talk is roughly as follows. I briefly shows a memristor-based neuromorphic device. It's very short, about just 1 minute. And after that, I show my research about direct observation of conductive paths, especially filamentary and also filamentary-free memristor. And after that, how can we improve the device based on the failure analysis? As you know, memristor-based neuromorphic device is very important to achieve, to overcome the limitation of von Neumann architecture. So many researchers try to develop the memristor-based, actually not memristor, develop the neuromorphic architecture. The memristor is one of the most promising candidates for developing next generation the device. However, if we design or develop fabricate memristor-based neuromorphic device, we have to choose the electrode and active material in case of two-terminal device. And also, we have to identify the mechanism of this memristor device because the mechanism totally depending on the material system. So also, and failure analysis is more important to improve the device performance. Normally, humans have a desire to directly observe the phenomena, some specific phenomena, their own eyes. So I also want to observe why this device shows this kind of performance. So we can easily directly observe the phenomenon of memristor device using two types of methods. The first one is piezoelectric driven needle types using in-situ TM holder, and the scheme is the real device. It seems like the right one. There is very narrow, just about 1 or 2 centimeter gap, and we can merge the device part left side, and also we mount the sharp needle type the right side. And we can make the device, nano device using F5E or maybe F5E. I only use F5E, but F5E. The bottom one shows the SEM image of nano device using F5E assisted sampling. In this case, they use the highly doped STO substrates, so they don't care about the cutting edge. But if you want to use the insulator substrate, you should connect the bottom electrode to the copper grid. In that case, they make them making the electrical path along the shaft tip and to grid. This approach has a very big advantage because we make multiple devices at a time, and also we can directly contact desired region using sharp tip. So we can make a local strong electric field specific regions. However, there is also limitations such as if we use the movable tip. So this movable tip press the device, so there is some stress-induced deformations. And also, normally we deposit the electrode about tens of nanometer over under 100 nanometers. So we cannot stop the metal line, so we have to deposit the platinum or conductive layer using F5E. But in F5, during the F5 deposition, there remains gallium ions. So if we under electric field, this gallium ion diffuses into our device. So there is some contamination issues. And also, as I mentioned, we make the nano device using F5E, and also we contact the sharp tip where we want to observe. So we only do that a highly experienced guy only. So compared to this, the piezo-driven needle type, MEMS chip-based type is more, I think, more easy to fabricate compared to previous one. And also, this type also have a very big advantage of stability because we don't need to sharp tip. We use the platform, so the device is very stable. There is no stress-induced deformation. However, chip is very expensive, and also, actually, we reuse the chip after removing the device and also contact part, but it's not easy, and the device can be easily broken. So there cost problem, there is some cost problem, and also the most important part is we can only one device at one time. So it's very time-consuming job. So normally we use the both device, and if you have a in-situ holder, you can try it many times. Actually, if we want to good data, I think at least 10 times or over 10 times you try. Yes, using this kind of in-situ TM holder, many people observe the atomic metallic filament inside the memristor device at atomic levels. In this study, they used silver is a easily ionized metal, so it can diffuse into the active layer on the electric field. Also, copper is similar to the silver, so many people try to use the copper and the silver because they can easily observe the atomic filament. But I think atomic filament is not good for application for the future neuromorphic device because silver and copper can easily self-annihilation and also self-diffuse inside. They move freely inside the active material. So I think this is not good approach for the future device. So I also observed some kind of filament, metallic filament inside the matrix, and this is a copper, and the right side is also copper, but the active layer is totally different. Not totally, just slightly different. The left side shows a strong and 20 nanometer width nanofilament inside the polymer matrix, and the right side is just a nanoparticle shaped filament inside the same material, but the ligand is totally different. So if you change the active matrix, even use the same electrode, the filament is totally different. So what is the next is filament-free memristor. Filament-free memristor means there is no strong metal bridge inside the matrix. Normally, people use this change the ion migration. In that case, people use the oxygen migration or nitrogen migration using some metal-rich or oxygen-poor phase. And also intercalation is, people may use, I think, some lithium or sodium, something like that, to easily intercalate the matrix. And also there are some other applications for filament-free memristor. I also studied some kind of filament-free memristor to observe the atomic scale, and the left side shows the graphene oxide and also oxygen ions can easily move to under electric field, and the crystallinity improved dramatically under electric field. And the right side shows the perovskite-based memristor and also oxygen. As you can see in the EDS mapping, oxygen moved to the downside under electric field and then makes the strong electric field inside the active layer, and also can act as a reservoir layer. The final stage is I'll just briefly show the failure analysis using electron microscope. Many people want why my device doesn't work well. So at the time we need to failure analysis. This SEM image shows the Brownhoff effect, and that device shows the permanent breakdown on the electric field, and that means this device does not work well, and we cannot use this device. How can we improve this device? We need to observe the cross-sectional image. The right image shows the metal protrusion inside the matrix, but I think this is not the real filament because electrode totally deformed under by-Joule heat. And also, I focused on the bottom interface that located between the bottom electrode and active layer. There is some bright contrast underneath of aluminum nitride layer that was confirmed by EDS mapping, that is a nitrogen-rich layer. And that means nitrogen moved under electric field that makes the delamination of active layers. So how can we improve this device based on the failure analysis? We need to control the nitrogen movement under electric field. So I make a bilayer structure that the first layer has a nitrogen poor and the second layer is nitrogen rich. So we can control the nitrogen movement using bilayer structure. And as you can see in the right side, the upper layer changed to highly crystallized aluminum nitride, as you can see in the image, and also HRTM and FFT image. And also the bottom layer, the nitrogen pure layer maintained wear. And if, this device shows the improved performance with a permanent breakdown. So in my talk, what I want to say is we need to characterize the device, and also we need to analyze the cause of the failure. Using this kind of method, we can improve the material and also device performance. Thank you for your attention.
Thank you for the nice talk. This is the end of first stage of this workshop, and after taking 10 minutes break, the second stage will start. So let's take the break.
Okay, sitting here is feels like I'm in the zoo, so being an animal. Okay, so I think it's about time. So this panel discussion, actually we have about 40 minutes to discuss about the questionnaires we already got before this talk concert meeting is planned. So probably it'll be easy. We start from this question to the speakers we got from this corps. So based on that, and also after that, we already listened to very nice 5 talks. So from the audience side, if you have any questions or want to ask some more from their presentation materials, now is the chance. Okay, so let's begin the panel discussion session. So again, my name is Seok Jeon from Korea University. So I'm really happy to bring all great researchers here. Okay, so actually we got one question from online, that what are the advantages of neuromorphic semiconductors compared to some now conventional HBM based or CXL based AI semiconductor chip, something like that. So actually Professor Yang showed us very interesting statistics that currently ChatGPT-4 requires $63 million of chips, and also daily cost of like operation cost can be approaching $0.7 million. So it is so expensive and so power consuming. So I'm pretty sure that this trend cannot continue. Like every 2 months, doubling is almost impossible. So from the standpoint, I think there must be some advantage of neuromorphic semiconductor. So can you share us about your vision? What is the advantage and what is the reason or driving force that this direction should go?
Yeah. Okay. Thank you for the question. So I think for neuromorphic computing, it has a different definition, and in the slide I showed, at least there are 2 types of computing people usually call it neuromorphic. The first one is the basic level, I would say. It has not much bio flavor in it. Rather, it is a in-memory computing, parallel computing, and analog computing. If you have these 3 components in it, it's already very efficient in terms of energy, in terms of time. So that's, I call it a basic level of neuromorphic computing, or many cases people call it a neuromorphic computing accelerator. Okay, that's one. The higher level is bio-inspired. It has more bio-flavor in it. It uses more neuron science principles than just in-memory, parallel, and analog. It has something else. Then it will be more efficient even in data. So learning could be much faster with much less data. Learning can be finished within a shorter time with fewer examples, but showing higher level of intelligence. That's, I call it more biorealistic neuromorphic computing. Okay, so we have these two levels. Then you compare to our conventional architecture, conventional structure. Now you heard of the ChatGPT, everything they are actually is running on a Van Neumann architecture, a digital system. And they are not in-memory computing. They are in parallel in terms of you have many GPTs, thousands of GPUs running together in that level of parallel, not the level of individual device. The massive millions, billions of devices running together. That level of parallel is the accelerator we are talking about. So basically, even if you use the most advanced hardware, like a high bandwidth memory and others, you can make it faster, but you cannot eliminate the fundamental Van Neumann bottleneck. It is still the Van Neumann architecture. You are still moving data frequently from memory and processor during the neural network model application. So that you just move it faster. It still costs a lot of energy. You do not really increase the energy efficiency as much. So I think fundamentally, we wanted to change the architecture from the Van Neumann architecture to non-Van Neumann to in-memory computing architecture, so that you can get the ultimate energy efficiency and the throughput. So that is what our brain is doing. And after we achieve that, then we can think a higher level with something close to natural intelligence. Our intelligence now is still way below what a real human brain can do. That is because we are not using the similar principles in learning, in computing. Okay, so in terms of when it can be commercialized, I think the first level, the accelerator, just to achieve those three principles. Again, in-memory computing, parallel computing, and analog computing. At that accelerator level, I would think it could be commercialized in the next few years. In fact, I also co-founded a startup company in the Bay Area, is working on this, and we are making chips, and we are making working demos. In the next few days, I will talk about that in detail in my presentation. You can see those are very close to real commercialization. And then the higher level, to build something really use a lot more neuroscience principles for higher level of intelligence, for higher level of efficiency, that is still very far. That could be, I don't know, maybe more than 10, 15 years, because that's limited by many things. One of the things is actually we don't really understand how much, how the brain really works. That is also one of the bigger challenge and also an interesting problem to work on. Yeah, I guess I will stop here to see if there is more.
Thank you very much. So any comments or question from the audience? Okay, if not, let's just continue. Okay, the second question we received was, is full analog system inevitable to replace SRAM-based NPU or TPU? And still, the analog to digital conversion or digital to analog conversion are the most power consuming component in memristor type based CIM. So is it really can be the answer to replace SRAM based NPU or TPU? So I think Professor Tae-Sik Yoon will be the good person to answer this question.
Yeah, I'm not sure I'm the right person to answer this question, but I just share my idea together. Where people are actually people try to use the SRAM, have been used the SRAM because it's a very reliable device. But SRAM has fundamentally some limitations. One of them is that is the most important one, critical one is that the low density. So if you use the only SRAM, and then it's very difficult to the computing memory system because the memory density is not that high. And then we have to use another memory which is outside of the computational unit. And then we will have this von Neumann-Bartlett problems. So because of those some limited density of SRAM, and then we have to use the more higher density memory device. And also SRAM has some binary operations. That is another issue there because we cannot increase the weight, synaptic weight state using only the SRAM. So that's the reason people are interested in the emerging devices like RRAM or PRAM or FRAM, etc. And then, my answer is that the SRAM has also some advantages of the good reliability and the high performance, but because of the low bit density and low weight density, so we have to use some higher density device. And then ADC and DAC are also very critical one because they consume a lot of power. So there is some research trend to develop the low power ADC and DAC. That is also very important subject that we have to develop. So many logic design guys try to develop the low power ADC and DAC. Also some people, some report or propose the system which does not use the ADC or DAC. So that is another field, another direction to minimize the power consumptions. So in principle, in order to solve the von Neumann-Bartlett problem, and also try to, in order to have this more high energy efficient computing in the processing memory or computing memory system, and then the use of higher density emerging device, emerging memory seems to be essential. If we use the only SRAM, and then we will have those von Neumann-Bartlett problem. So SRAM can be used in some part, but many part for the high memory density part, and then emerging memory device would be a good candidate. And ADC and DAC should be developed further to reduce the power consumptions. And then other solution where to have because in order to have the more energy efficient computing, and we need a high chip density, high memory density, even use some RRAM or PRAM or emerging devices. So 3D integration would be some essential part, I think, because we have to integrate the process and memory together as close as possible. And then we have to increase the chip and memory density as many as possible. So the 3D integration would be some viable and essential solution to improve the computing efficiency in the computing memory. Yeah, that's it.
This is a good question. You think SRAM, right? You need at least 6 or sometimes even 8 transistors to represent 1 bit information. And for most of the inference, you need 8 bit, just for 1 weight. So then how many SRAM you need? But if you go to the emerging memory like RAM, we have shown we can get 11 bit per cell. And so this is at least 48 times denser, right? That's just by doing this calculation. Then as this is 2D. And then the new memory, you can do 3D integration. SRAM, you can only do chip level of stacking. So this is for density argument. Not only density. When you do a neural network, density is only one thing. The most important thing is the connectivity. So if you do 3D, then you have the connectivity you need to make a complex neural network. And if only 2D, you will never get the connectivity complexment. Okay, our brain actually is 3D. So that's also from the connectivity point of view. Then from the non-volatility point of view, especially for the edge applications, you do not want to keep your power always on to keep the weights, which is SRAM. You have to keep the power on, turn off the power, the weights are gone. You have to have a non-volatile memory to store the weights. So that's for edge application almost impossible, right? So that's from non-volatility point of view. So from all this, the reason people use SRAM is just because it's available. It is available now, you can use it. But that not necessarily mean it's the best device to use for this purpose. So that's why I always say, this is like a problem. You want to nail down a nail, on the board. You want to nail down a nail. You don't have a hammer. You say, I have a wrench. That's SRAM. If you use a wrench, you can nail down the nail as well, but that's not the best tool. If you have a lot of nails you need to nail down, you better make your hammer to do it, right? The hammer is the new type of memory, such as RM or memristors. That's my view on this, but especially for edge applications. Okay.
Thank you very much. Yes, so yeah, those two questions also kind of connected. So yes, so in some sense, yeah, we must find out some new way. Okay, so the third question I found is, what is the most difficulty developing the spike neural network system at current stage? So how many years does SNN take to be mature technology? So I'm not sure, maybe this is coming from industry or students. I think Professor Lee, Kyusang Lee, may be the good person to answer this question.
Okay, this is very interesting question. So spiking neural networks is basically using the short-term plasticity. And then what is done is that we are taking advantage of the frequency domain instead of the intensity of the signal. So this is not an easy system because the current, like the digital system, we are using the 0 to 1. And then analog computing system, so we have using the multiple state. This is even harder because we are changing this intensity from the intensity domain to the time domain, which means that we need to dealing with this frequency. So we need a much more complicated peripheral circuit. And in my point of view, it's mostly depending on the industrial need or the end user need. So conventionally, these days, so people use convolution neural network heavily. So CNN is the one of the neural network we are using. But as you might know, OpenAI, they are using this large language model, so which means it's kind of the trend. So where is the most of the end users? For example, the computer scientist, algorithm, and then architecture, they think that they apply this large language model in the hardware side, and then they figured out this is very efficient for many different type of application, which means that in terms of the hardware, so people trying to meet their need, which means that we need a lot of the high density memory. That's why we need the high bandwidth memory to kind of operate this memory combined with the silicon-based transformers. It's mostly, I believe, that depending on the how heavily this industry or the end user want to use the SNN to mature this technology. So I think the question, how many years does SNN will take to mature? So I think that it will be depending on the need from the industry. That's kind of my point of view. For the how difficult developing the SNN, so most of common way to develop the SNN hardware is they are using the CMOS. But there is also the effort to develop this SNN system using the emerging materials such as the niobium-based kind of memristor device as well. But it's still the early stage, so I think the developing the component for the SNN is also very premature at this stage. So that's my understanding. If anyone want to add, so I would be very happy to listen.
Yeah, I can add some. So the reason we are interested in SNN is because we believe our brain is using something more like SNN, right? However, as I said, we don't really know much about how the brain works. That's why we only know very few things, how SNN work, how to train the SNN. The algorithm is still one of the biggest challenge. We don't really know how to train an SNN neural network with a large size. We only know something like STDP, spike timing dependent plasticity, which is a local training algorithm. It's not like backpropagation. You can train a large neural network model easily. So the algorithm to train a SNN at a large scale is, in my view, the biggest challenge now. Because we don't know what we need. If we don't know algorithm, we don't know the device, what kind of device we need. So then at the device level, what we do at this moment is only to emulate individual devices, such as how it spike, the spike frequency or spike timing. So we only demonstrate STDP with a few devices, and not training a large network. So even though there are some SNN large neural network like the Loihi, they are Loihi 1, Loihi 2, they are still using the CMOS devices. They are still kind of a simulation of SNN, not an emulation. Yeah, so it's still a Van Neumann architecture at the root. So yeah, in a short nod, the algorithm is still unknown to train large SNN network. With that, what kind of ideal device we need, we don't know. So it's still long way to go. We know it is good. That is what we know.
Yes.
Let me add
Sure.
one more thing. And so for the device point of view and the materials point of view, I think the easiest way is that if you want to make some unchangeable device, and that would be the easiest way, because we have to try to minimize the defect state, and then you can minimize some factors that change the device. That's the way actually the people have been doing to develop the silicon technology. And then another thing is that if you make some non-volatile device, and that would be maybe the next easiest way, because you have to make some unchangeable stable filament, for example, or if you're using this phase changing materials, and if you change the phase of the material, and you can have a more non-volatile properties of the device. But for some short-term plasticity based SNN, and you have to control some time-dependent decay characteristics of the changed state. And then that would be a little bit more difficult. But I think it can be done because we know there's some diffusion dynamics and then some charge detrapping dynamics, for example. And so there's no fundamental limit. But I said it's a little bit more difficult than the conventional silicon technology or non-volatile device. But we may be able to if you keep studying. Yeah.
Thank you for the comments. Okay, so yeah, many of the answers we still don't know. We still don't know brain. So, but yeah, we are here. So actually also the other questions I can find out is number 5, 6, 7, 8, actually some stability issue of filament type material and also perovskite material, endurance of the material, and how about the 2D material. So actually it's very interesting. So when I was a graduate student, I mean, just remember, actually our BrainLink meeting, we have very many material scientists here. So I remember the first transistor made at Bell Lab was not actually silicon, it was germanium, right? And also, around that time, one of the Nobel Prize winner, he said, silicon is so dirty material, nobody can make transistor out of it. So probably I think we are around that time. So I think the material science should take the lead and then continue to learn this neuromorphic or memristor, whatever type of neuromorphic devices. So in that sense, I think young faculties, they are working on this material side will be probably very informative ones. So maybe can I ask question number 8 to Professor Joo-Hoon Kang, that what is the reality from the perspective of equipment and boundaries for the commercialization of 2D materials? So can you answer?
Okay, thank you very much for your question. I didn't realize that you're gonna skip all the questions in the middle. So I'm trying to arrange in my head. But I guess my answer for this number 8 question is that it depends, because nothing fixed yet for everything, because in particular for to describe the reality of the equipment foundries for the commercialization of 2D materials, we have to fix what kind of materials we're gonna use and which application we're gonna use. Then we're gonna narrow down what kind of equipment and the foundries we can utilize for that purposes. Let's say as I introduced during my talk, if you're gonna use the solution-based processing, then the equipment and the foundries, nothing special, like just a large beaker, you can produce the large amount of materials. That's it. But the particular direction for this commercialization of 2D materials synthesis is that the MOCVD, which can produce high quality 2D materials in a large area, wafer scale. But that MOCVD is also still satisfying the quality of the materials, but still it's not satisfying some point of view. Like for example, the synthesis temperature is too high, so sometimes the back end of line is not comparable with the synthesis method, and also it should be transferred from the mother wafer. So that kind of the aspects still make 2D materials commercialization challenging. And also during my talk also I define several challenges to commercialize 2D materials in the real world applications, which is the identical meaning of the requirement of the industrial level synthesis. Like quality of the material is very important, and also what kind of a semiconductor you're gonna make, you're gonna use for that special purposes. And also especially the semiconducting material, semiconducting 2D material most of the semiconducting material is like a multi-element compound. So you have to control the stoichiometry very precisely. And in these purposes, you also have to precisely control over the amount of the precursors when we make it based on the MOCVD, like a chemical vapor deposition method. So in sum, my point is that we don't know yet. So 2D materials commercialization purposes, we have to think about the material and purpose of that, the final goal of that applications. Then we're gonna know the equipment and the foundries. But of course, the solution processing just need a beaker, but the MOCVD needs like a large amount of quite complicated equipment. But for example, like a EUV lithography system, which is almost it's very difficult and it's very challenging to make equipment itself, but ultimately people make it. So likewise, I think if we can fix certain 2D materials for certain purposes in electronic devices applications, then we're going to make the equipment and the foundries at that point. That's my kind of answer. Yeah, thank you.
Anyone want to add? No?
Yeah, so since we have so many mature scientists here, yeah. So as Professor John just mentioned, materials play critical role in neuromorphic, in microelectronics in general. So I came from Silicon Valley, as Professor John just said, the first transistor actually was made out of germanium. And people wanted to make germanium transistors instead of silicon because it has a higher mobility than silicon. But why it ended up with a Silicon Valley, not a germanium valley? Why we were not using germanium? That is because germanium oxide is water soluble. It's not stable oxide. So silicon dioxide turned out to be fantastic. And that is why silicon win, and it becomes Silicon Valley. So those materials issues, even very little difference can actually determine the future, make a huge influence on the industry, on the application. So it's the material scientist here going to play a very important role.
Germanium Valley sounds weird, right? Okay, so also there's another question about the materials. So actually, I also recently see lots of halide perovskite materials applied to neuromorphic devices. So I think Professor Dong-Hae Kim here, one of the world expert in halide perovskite materials, maybe he can answer this question. Can you?
Thank you for introducing. Actually, my name is Dong-Hae Kim from Korea University, and actually I'm working on the perovskite material especially on the solar cell application. And also during my research period, I also make interesting on the other application using this kind of the organo and inorgano halide perovskite material, such as the memristor or photodetector and the other kind of the LED kind of things. And also, several study, some small project I also participated to fabricate the memristor application. And at the time, due to the perovskite crystal structure, they have a very good ability to ion migration. So it is very good candidate to make it the memristor application, I thought. But still, there is some kind of issue still remain. There are many kind of the perovskite person are working on the solar cell application. So it means the solar cell application actually developed like a large area coating, but without any void or very fully covered one. But in this application, when I tried to make it, it's required such as a patterning or the other kind of the very precious alignment within the electrode material. So that kind of a direction is a totally different way compared with the solar cell application. So technically, this direction is many perovskite person is focusing on the large area and fully covered without any kind of the patterning part. But nowadays, some part like a LED or the memristor, that part is developing. So they're giving a good result. So I think that kind of part will, that kind of the expert, the result will cover about and will show some good progress to apply this material to apply the memristor, neuromorphic memristor computing field. And also, but another issue in terms of the material property itself, during the the filament generation, because of the the metal electrode can make a reaction between the halide material or the other A-site cation part. So that is that can make another issue too, because during that kind of the filament generation and the reaction during the voltage is on and off reaction. During that time, that kind of the uncertain, unwanted reaction is generated. So the material scientists should solve that kind of the issue, like the more higher energy or higher bond energy. If we generate that kind of the strong, more solid perovskite material, then their reliability should be increased. So at the first time of the perovskite material is reported as a solar cell material, they just show the 4 hours stability. But nowadays, its solubility, the stability already reached around over the 1,000 hours. So this kind of material have a very, very large room to improve their crystal property. I thought like that. So due to that kind of the reason, when I summarized the overall that kind of property, I pretty sure these materials can give a good chance to another option to make it, to develop the next generation neuromorphic device. Okay, yeah, that is my opinion actually.
Okay, so also I found one interesting question. I'm very interested in neuromorphic semiconductors. However, I'm not sure which courses I should take during my undergraduate studies to help me in this field. Are there any recommended or essential major courses? Is there any undergraduate student in the audience? Please raise your hand. Oh, you? So you made this question? Okay, honestly speaking, all of the professors here, when you are in undergraduate student, we never heard about neuromorphic devices. But now you have some study, especially Professor Joshua Yang and everybody here, probably you have your own perspective. What kind of courses you should listen to, or what will be very helpful. I'm pretty sure Joshua will say you should take some neuroscience, something like that. But anyway, so maybe in turns we can answer what class we should, like the question number 4. Even the graduate student will be very beneficial to listen to this. Could you read?
Yeah, sure. Yeah, as actually you said, my first recommendation is neuroscience courses. Yeah. So as you already know, that is important for the higher level of neuromorphic computing. And then for the accelerator type of neuromorphic computing, so I would recommend people take some circuit course, analog circuit, mixed circuit design. That will be very helpful. As we already heard, in the questions, the ADC, DAC, those type of circuit become the bottleneck eventually, because our neuromorphic system usually need to be put in the system working with some digital system. Then even if your memristor crossbar array costs 0 energy, and the interface circuit, ADC, DAC, if they cost a significant amount of energy, then this is not a good system. So yeah, then the circuit course. And in fact, at USC, I'm teaching a course designed for this purpose, covering from materials to some circuit to architecture and algorithm. So that usually it's probably not for under, it is only for graduate student. So I'm sure there will be more courses like that at the graduate level in major universities. Yeah.
Okay, so my background is electrical engineering, and then I also kind of affiliate with the material science. My recommendation is basically the solid state physics or the solid state device or condensed matter physics. So those are the very basic kind of the courses that can branch out to the many different type of the device or the kind of even the application. And I believe those will kind of enhance your kind of background toward the neuromorphic computing or any semiconductor-based device. So my recommendation is the solid-state device. It helped me a lot as well.
I agree. Okay, if I choose one courses, and then I recommend the kind of defect chemistry, because we try to connect and utilize these material properties depending on these defects, because in the case of some memristor or phase change memory or FRAM, and then all the properties are related to the defect. So if you understand how the defects and how the material structures affect on the electrical property, and that would be very good for you guys to understand the device operations.
The answer will be more difficult to decide.
Then I'd like to change my scheme. Then since all the professors introduced the good courses which can be helpful for the understanding of neuromorphic semiconductors, my recommendation is one well-written review article with YouTube, because this is like a fancy a research field, not like a conventional research field, like a research field with the old-fashioned. These kind of things are very well described in the review article, like a high-impact journal, like a Nature subjournals or something. The well-written review article will be helpful, and there still have many questions, like which terminology describe what or something. So in that cases, you can refer to the YouTube videos. Then there are so many informative video clips in there. So for example, I also take a look at the analog circuit textbook, but there's not enough time to see all the things in detail. So instead of that, I'm trying to find out the essential course of the circuit on YouTube video, or some other open courses, like Stanford University also release several open courses in Coursera or something. So you just can find out by Googling. Okay, thanks.
How about ChatGPT?
So it's my turn, and I'm not sure, but in my opinion, I would like to recommend the class related to the metals. Actually, some metal or phase transformation or something like this, because MSc starts from the metals, so metal is very core class in MSc department, and every material is based on the metal. Even electrode, and also the active material or 2D material is based on the metals. So if you learn about the metal formation or nucleation growth, that can apply the other field. So I think the metal related field is very important in MSc field. So that's my opinion. Thank you.
You want to stop there? Okay, so yeah, I think the older professors answer, if you combine, you take all the courses, okay? Actually, Professor In-Han Lee actually recently awarded the 3.5 years, $11 million US dollars project of AI specialized semiconductor program in Korea University. So actually, I think he shared this vision, and then maybe you should construct this course soon, right? Also, okay, so I think we have only about 10 minutes to go. So probably from the audience side, you must have some question or unanswered parts. So it's okay if you can ask a question in Korean. Maybe I can translate and then transfer to the speaker. So if you have any question, please feel free to raise your hand. And how stupid the question is okay. I mean, sometimes those questions are the best question. Okay.
Thank you for Professor Yang. It is a very simple yet yet critical question. Since you mentioned you're planning some commercialization of memristor, so I'd like to ask what kind of reliability criteria is most critical for commercializing the memristor, and how do you planning to stabilize and harnessing the stochasticity for those unreliable characteristics?
Okay, that's a very good question and important question, as you said. So yeah, you can see it. So the question is, what are the most important property, and how do you overcome the reliability issue for whatever, the first commercialization application? Okay, so this is a heavily application dependent. So for the first commercialization, we are picking the low-hanging fruit of this technology. So the low-hanging fruit application, in my view, is inference application on the edge to accelerate machine learning. Okay, so that means some of the problem you usually think is memristor or RM. It may not be a problem for this application. For example, everybody knows the stochasticity, the switching from cycle to cycle, from device to device, they may not be the same. If you use the same operation, you may not get the same switching resistance level. That is a problem for memory application. But that is not necessarily a problem for the application I'm talking about. The reason is when you use it for memory, you give it one switching pulse. You want it to switch to the target conductance. Otherwise, you get an error. You will have a very high bit error rate. That is not allowed for memory application. But for edge inference application, usually you just program the device once to the conductance level, then you just use it for inference. Use it for inference meaning just reading the conductance over again. You don't switch it anymore. So you can afford to use switch, then read it to see if you get your target value or not. If not, you do it again. So you can do many iterations to get the target conductance level you want. After that, you just use it for inference. So that's why you can afford, you have time, you have the energy, you can afford to do many of those iterations to switch to the target level that can overcome the stochasticity or the reliability issue. Okay, so that means the stochasticity in switching is not a problem, but you will need the device conductance level to stay there for a long time without changing. That becomes very important, right? So then you need to do a trade-off. So even though your switching can take many cycles, a lot of energy, but after switching to the target level, it will not change over time. That stability is very important. So that again means the trade-off in the materials selection, in the process selection to reach this goal. You have to know the trade-offs. So fortunately, there are materials that allow you to switch the device to the level and stay there forever, even at an elevated temperature. So the trade-off key parameter is the activation energy for the ion to move. If you choose activation energy high, then it takes a higher energy to switch, which is not good for memory application. But for the inference application, you do not switch it often. It's okay to take more energy to switch it. But because the high activation energy, after switching, it will stay there for a long time without changing. In other words, high retention. That become critical. So once you make the right material selection, you will see those properties. You can use it for edge inference application that can make the first commercial product. So again, materials is important once you understand what you want. You can select the materials and the process to get what you want and make the product. In fact, in the startup, we are making 12-inch wafers, millions, billions of devices, and across the entire wafer, you can randomly choose a device to switch it to a target level. You can choose one device from each die and switch it to the same target level. You can see very narrow distribution. But each device, you need to do the iteration of switch, then read to see if you get the conductance level or not, something like that. You need more energy and time in switching to the target level, which is fun, because you do not switch it very often for inference application. And then for other applications, you will need to do other type of trade-off. Then you select the different materials and the process to do it. Yeah.
Okay, so, okay. Oh, they are very active.
I'm a student from UNIST, and I have a question, same question with pre-asked question. Is it possible to create synapse array without ADC and DAC? If the memristor has ohmic behavior, you can modulate input and output signal as analog order. But current memristor, most of current memristor has non-linear TIV behavior, so we cannot control that input. We need ADC and DAC. So is it possible is it possible in architecture level if we have a linear memristor?
So my understanding is kind of two questions. First, can you build the chip without ADC, DAC? Second is it possible to make the memristor linear current voltage relation, or if you have a nonlinear current voltage relation, how do you use it, right? So the reason you wanted to use ADC, DAC are at least for two reasons. First is you wanted to build an accelerator that is compatible to a larger system. A larger system usually is digital. And so then you will need the input, output, deal with the digital signal. That's why you need ADC and DAC. However, for a system that interface with the sensors, usually that's where the raw data coming from, and the sensors usually is an analog system, and if our accelerator directly process the sensor signal, we have the chance to remove the DAC because we directly get analog data, which saves a lot, time and energy. And if the output, the system is not too large, so you can try to do a communication within the analog domain, then from one chip to the other, you can probably communicate directly or put your signal in analog domain to the next level. But that probably is not going to be a very large system, because for long distance communication, you probably still need a digital system, because you do not have the error accumulation, which is a common issue in the analog system. So I my feeling is probably you can have a few layers communication within analog domain, but not more than, not a lot, because the communication have to be done in a digital domain. If you think our brain, the spiking signal, it's hard to say it's analog. Actually, the spiking signal is more like a digital because it's a full communication. And if you look at the axon, the spike signal is going to decay over distance, but then it is reboot in the axon and to recover the signal in the spike. So it's still, we do not know a way to communicate for a long distance in analog domain. So I think it's, unfortunately, we still do not have a good solution, to remove ADC totally. But the good thing is the ADC, people now have a quite fast ADC, gigahertz, 10 gigahertz, so it can be shared by many columns, so that they save, some space. Then the second question, for the device nonlinearity, usually you will find that if you make the device at a low conductance level, a low conductance, high resistance, usually it's nonlinear, right? If it's below the quantum conductance, below 12 kilo ohm, usually you can get a better linear current voltage relation. So if you like your device, but it has a nonlinear IV curve, nonlinear current voltage relation, so you usually use it in a different way. You rather, your input voltage amplitude usually is what you use, the amplitude of the voltage. Instead, you can just use pulse with the same amplitude, but a different number of pulses to represent your number, input number. Or you use a different width of the pulse, but they have the same height. All the pulses have the same height. Then you can use a nonlinear memristor to represent your weight. So that is doable, but of course you sacrifice the time. So now with instead of just use one spike to represent a number, if the number is large, you need many spikes or a long width. So you have to make your circuit faster. Okay, so the analog circuit, how to make it faster? There are a few things, like how do you design your TIA to settle down quicker, and how do you sense the current in a different way to make it faster? There are some solutions. Yeah. Okay.
Thank you. I have just one more question about. I wonder the difference between electrical breakdown and filament formation. Actually, electrical breakdown is common characteristic in electronics or arc discharging like thunder. But filament formation is a little specific property in CBRAM. So can we say electric breakdown and filament formation as same thing? If not, is there any possible evaluation to evaluate the speed of CBRAM?
So, I can take the first step and then let others to add. So if you talk about the traditional oxide anion or valence change type of devices, I would say the electrical breakdown, the electrical formation is more like a soft breakdown. So it is a process to create oxygen vacancies in the device. The memristor or device is a defect business, and so you need to create the defect first if it's not already there. Okay, so that's why you first need to do a soft breakdown. But if you already have the built-in oxygen vacancies in the film, for example, you have a substoichiometric oxide, then you will find the electrical forming is much less drastic. It is more like a forming-free device because you already have the oxygen vacancy defect there. So when you do a soft breakdown, it is more or less the same. You are creating some oxygen vacancy defect in it. So in that sense, it's very similar. But it's a soft breakdown. It is, in some sense, it's reversible. Usually your hard breakdown is not reversible. But this is reversible only partially inside the filament. For a CB, that's for a valence change type. For a CB-RAM, you are injecting the electrically, chemically active metal ions in it, like copper, silver, into the film. So that is not a typical breakdown, right? But you're injecting those. Yeah, okay. I don't know if others want to add.
Yeah, let me add one more thing. Actually, it's the same thing. Actually, already the Professor Yang mentioned. If the insulator flow the current and it is broke down already, and so if you use the RLM device, and then the RLM operation is using the breakdown, that is the so-called low resistance state. But the thing the important in the RLM is it is reversible. So you can make a high resistance state, and you can change the low resistance reversibly. So basically, we use the defect distributions to make a breakdown intentionally and then recover it intentionally, and then you can change the state. So actually, there is a breakdown phenomena.
Okay, I think we are 10 minutes beyond the schedule. So yeah, I think there are just one more quick question. Okay, this is the last question.
Okay, thank you all professors for great presentation and talk. I have questions for a general context of neuromorphic systems and devices. Most of AI models such as LLM and transformer like Llama and Gemini and ChatGPT, such as etc. They use just backpropagation in inference process, but our brains not use backpropagation. Our brains just firing and so on. Use backpropagation, but neuromorphic system and devices use a keyword of bio inspirations or by brain mimic something, but the software realm and hardware basis system is not quite feasible for this keyword. So I just would like to listen opinions the professors for these bottlenecks aside from the polynomial bottlenecks.
I'm not sure I understand the question. Yeah, in the consent sentence, what is really your question?
So our brains just use the firing system, so we do not use the backpropagation. So just the electrical potential, just the firing, just the front synapse and neuron. But our software system is just use backpropagation for the inference process. But our neuromorphic system and device use a keyword, bio-inspired or brain mimics something. But this is just not feasible for using neuromorphic systems to software and the hardware systems to connect with neuromorphic device and system. So I just would like to listen to the professor's opinion and the vision, something this gap or to dilemma.
So is your question is like kind of spike neural network and then compared to the current one, or I mean?
It seems like it's a spike neural network. So
actually, it's, again, the question of SNN. Honestly speaking, I think we already answered that. Yeah, there's difficulties, and also, so can you summarize?
I still sorry. I still don't really understand your question. Maybe your question is our current AI is very different from the brain. Yeah, and the current machine learning using backpropagation. In our brain, we're using something more like a unsupervised learning. So I guess your question is, I still don't know what's the question really. So.
Can you really make this brain-like functioning computer? That's kind of somewhat
yeah, sorry. I'm trying to see, what you really want to know.
네. 간단하게 말씀드리면은 이제 우리 뇌가 이제 그냥 어떤 신경 와이어링을 하게 되는데 그게 에서는 소프트웨어가 한번 학습을 하고 다시 추론을 할 때 이제 백프로파게이션을 사용을 하게 되는데 근데 이게 저희의 브레인과는 사실 약간 다른 어떤 시스템을 갖고 있다 생각해가지고 하드웨어 시스템에서는 이제 아날로그 스테이트나 이제 멀티플 스테이트를 가지면서 어떤 뉴로모픽이라는 키워드에 맞게끔이라고 생각이 들었는데 소프트웨어 쪽에서는 많이 사용하고 하드웨어 쪽과 소프트웨어 쪽이 아직 잘 이어지지 않는가 싶어서 이 질문을 드린 거거든요. 완전히 뉴로모픽한 시스템을 만들기 위해서는.
So I think his question is, in hardware-wise, we are following the neuromorphic, but software-wise, actually, it's not the same algorithm or something like that. So I think the biggest problem there is because currently most of the software they are built on the digital algorithm, and then just using that algorithm directly to connect to current neuromorphic is actually not bridging well. So we are just modifying and just connecting it. Probably, so the architecture, Professor Yang already mentioned, the software itself also should be changed to adapt this new neuromorphic system. So I think software is a long way to go. Yeah. Is it answer? Okay, so I think it's time to wrap up today's meeting. Okay, so let's thank all our panelists here. Thank you very much for your answers, and thank you very much for your active participation. Okay, I want to close today's brain talks. Thank you.